Welcome! In this lesson I will introduce a general and important issue with disproportionality analysis and one way to resolve that issue. To get us started, consider these two different situations. In the first one we have a drug event combination with 2 reports observed and 0.01 expected, and in the other one we have a drug event combination with 20 reports and 0.1 expected. As you see, the observed to expected ratio is the same for both of these drug event combinations. It's 200. So the reporting on both of these combinations appears to be highly disproportional. However, in practice, these situations are quite different. First of all, it's generally much less likely that a combination with 2 reports would end up as a signal compared to one with 20 reports. And secondly, the weight of the evidence from just 2 reports is in general not particularly high, even though it can yield very high disproportionality, as in this example. This problem is due to something we might call random variability. If the expected number of reports is really low, like 0.01 in this example, it's sufficient with just a few reports, like 2 here, to obtain a really high value of disproportionality. But in reality, we could obtain a few reports on any drug event combination, just by chance, even if there is no causal link between the drug and the event. So if we take observed to expected ratios at their crude face value, we run a clear risk of detecting a lot of false associations just by chance. There are different ways to handle this issue, and the one that I'm going to present here is the one that we recommend, and the one that we've also been using in our own disproportionality analysis on Vigibase for a long time. The underlying theory is mathematically quite complex, but actually the end result is rather straightforward. One part of the solution is something we call shrinkage, which we can think of as adding half an imaginary report both to the observed and to the expected numbers of reports. And as you see, with this little trick, we pull down the observed to expected ratios for both of these combinations, and the pull is much stronger for the combination with just 2 reports, which is the one that has less data. And these new numbers, 4.9 and 34 respectively, much better reflect our intuition that probably the strength of the evidence is stronger for the combination with 20 reports. And now I'll use another little trick and move these values to a log scale. And the main purpose of doing that is that it becomes easier to compare high and low values of disproportionality. If we use a log 2 scale, like I've done here, we get the values 2.3 and 5.1 respectively. And with a log 2 scale, and with an expected number of reports that is computed as we do for the relative reporting ratio, the result we get is something we call an IC value, where IC is for information component. And this is one of the common measures of disproportionality and the one that we use here at UMC. This scale may seem confusing at first, but it's actually not that difficult to interpret. If the IC is equal to 0, we use here at UMC. This scale may seem confusing at first, but it's actually not that difficult to interpret. If the IC is equal to 0, that means the observed is equal to the expected. And if the IC is 1, that means the observed is twice the expected. And then for each step that the IC increases, the observed to expected ratio is doubled. So if the IC is 2, that means the observed is 4 times the expected, and if it's 3, that means the observed is 8 times the expected, and so on. Now, let's get back to our example. You may recall that we have 2 drug event combinations, one that has 2 reports and one that has 20 reports, and that the observed to expected ratio is the same for both of them. It's 200, which is just below 8 on a log 2 scale. If we then apply the shrinkage, which means we compute IC values, both combinations are pulled down, as we noted before. And again, the less data there is, the stronger the pull, which is very obvious in this example. However, the shrinkage alone is not enough. Even if we don't quite trust the evidence for the combination with just 2 reports, it still looks disproportional. As you see, the IC is still above 0, so the observed is still greater than the expected. And this is where the second part of our solution comes in, the uncertainty intervals. For normal use, we recommend to compute 95% uncertainty intervals around the IC, which is what I've done here as well. And the most important thing to know about these intervals is that they provide additional protection against detecting false associations. And the more data there is, the more we trust that disproportionality analysis calculation, which results in shorter intervals. And in this example, you see that the combination with 20 reports has more data and therefore a shorter interval. The other combination, the one with 2 reports, you see now has a lower endpoint of its uncertainty interval that is below 0. This means that after we have handled the issue of random variability, we are no longer confident that the data is sufficient to say that it is disproportionately reported. So in short, the IC, or the information component, has 2 main features, shrinkage and uncertainty intervals, that together provide good protection against detecting false associations when disproportionality looks high but is based on just few reports.